Please welcome a program manager from DARPA's Information Innovation Office, Dr. Matt Turek.
Thank you. When you look at an image or video online, can you tell if it's been manipulated or not? If you could, would that alter your opinion of it? Today I'm going to talk to you about the work on DARPA's media forensics program and our ability to automatically detect manipulated media. I'd like to start with a historical perspective, and so I'm going to begin the story in the early 1800s. The first commercial photography process, daguerreotyping, became available around 1835. Matthew Brady was one of the first commercial photographers in the United States, and he later became famous for his Civil War photography. He took an early image of a Southern politician, John C. Calhoun, that turned into a mezzotint print for a book, and that's displayed on the right-hand side. Thomas Hicks, who was a portrait painter, was seeking to create a more heroic-looking image of Abraham Lincoln around the time of the Civil War. So Thomas Hicks took the image of John Calhoun and repurposed it, combined it with another Matthew Brady photo, this time of Abraham Lincoln's head, and used that to create the image that's located on the left-hand side. So compositing of images was used commercially as well. So this image was of Ulysses S. Grant and was created in the early 1900s. And the image on the right-hand side is actually a composite of parts of 3 images on the left-hand side. The photographer in this case was Elsie Handy, who happened to be the nephew and apprentice of Matthew Brady. And what Elsie Handy was seeking to do was to monetize the large collection of Civil War photographs that he had inherited from his uncle. And he found that by constructing more compelling composites, he was able to sell them more easily. Even talented young photographers had the ability to manipulate images. In 1917, the first in a series of photographs known as the Cottingley Fairies was created by 2 young cousins, Elsie Wright, who was 16, and Frances Griffiths, 9. And it started as a practical joke on Frances's parents. They had scolded her when she told them that she fell into the creek playing with fairies. And so the 2 young ladies cut images of fairies out of a child's book, stuck them on hat pins, and included them in photographs. They didn't actually fool Frances's parents. But they created other photographs that came to the attention of Sir Arthur Conan Doyle. He published them as real, and they got significant attention in the early 1920s. We might think of this as going viral today. Even though experts from film companies like Ilford and Kodak looked at the images, they would not definitively state that they had been manufactured or manipulated. And it took until about 1983 when the ladies finally came clean about how the images had been constructed. Manipulation of photographs took a darker turn in the run-up to World War II. In this case, Joseph Stalin had an army of photo retouchers at his disposal. And this example is of Nikolai Yezhov, who was a secret police official who later fell out of favor, and he was executed. Stalin used that army of photo retouchers to remove him from the photographic record. They used darkroom techniques and airbrushing to do that, and you can see the result on the right-hand side. After World War II, we saw the beginnings of the digital technologies that we have today. This might be the first computer-generated animation, and it shows a road outside of Stockholm, Sweden. It was created by the Royal Swedish Road and Water Construction Agency on one of the world's first digital computers. And it required an oscilloscope and an electronically triggered 35mm film camera to produce. In 1975, Kodak created the first prototype digital camera. It was the size of a large toaster, weighed in excess of 9 pounds, and took over 20 seconds to acquire an image. That image had 1/1000th the resolution that your cell phone can take today. And of course, it stored it on the medium of the day, an audio cassette tape. A few years later, IBM released the personal computer, starting the personal computer revolution. It had a 4 megahertz processor and ran the Microsoft DOS operating system. These sorts of technologies made their way into the film and entertainment industry as well, as illustrated by these 3 Academy Award winners. In 1977, Star Wars won an Academy Award for a sequence known as the Trench Run briefing, where they used a wireframe of the Death Star as part of the briefing for the rebel pilots who were attacking it. 12 years later, The Abyss used a much more sophisticated graphics technique to generate a water pseudopod. There were 75 seconds of this special effect in the film, but it took over 8 months' worth of work to produce. And then in 1993, Jurassic Park came out. There were 14 minutes worth of dinosaurs in the film, 4 of which were done with computer graphics and 10 from animatronics. The switch to computer graphics was actually a change in plan. They were originally going to use stop-action animation. And this was the first large integration of computer graphics and live action in film. In the early 2000s and mid-2000s, we saw 3 key technologies that have really accelerated the AI revolution that we have today. The first is GPUs, or graphics processing units. They provide highly parallelized accelerated computing in a compact, inexpensive form factor. The second technology was the rise of large data sets, as illustrated here by ImageNet. This was created to further research in the computer vision community, such as object detection and image classification. It contains millions of manually labeled examples across thousands of classes. And then, in 2012, a breakthrough in performance in image classification, AlexNet. It used a deep learning technique for the large-scale visual recognition challenge that uses ImageNet. It provided such a significant gain in performance that has essentially reshaped the computer vision community. Most of the state-of-the-art techniques now in computer vision use deep learning in some form. 2 years after AlexNet was published, Ian Goodfellow published a paper on generative adversarial networks, or GANs. And GANs are broadly applicable. They give us new ways to train deep networks. They give us ways to generate synthetic data for training or for other uses. What's most relevant, perhaps, to the media forensics community is the ability to generate synthetic faces with GANs. And you can see the dramatic progress that's occurred just in a few years. In the initial paper, a black and white, low-resolution, blurry image of a human face. On the right-hand side, photorealistic faces. And there's even newer techniques than this. An NVIDIA paper published at the end of 2018 showed detailed control of facial features, such as the pores in the skin. So all the people on this slide never existed. They were all created with GANs, or AI techniques. We've seen similar progress in the ability to manipulate video as well. In 2016, an approach called face-to-face was published. And this uses real-time tracking to monitor both a source and a target face and to transfer expressions across them. And then at the end of 2017 and the beginning of 2018, deepfakes came out. This is a deep learning approach to swapping faces into videos. And it was quickly used by the internet community to swap faces of actors, such as Nicolas Cage, into movies in which they never starred. So consider the rate of change. It took about 80 years to go from the beginnings of photography to the point at which 2 low-resource users, Elsie and Francis, could create a compelling manipulation. Compare that with the progress in GANs. In 4 years, we've gone from blurry to photorealistic faces. The pace of technological change now is breathtaking and has the potential for significant impacts on society. So what does it take to create a deepfake? You'll need a few thousand frames of training data, both for the source face and for the target face, and you'll need access to the neural network software that will perform the swapping. But it has to be trained for those individual faces. And so to do that, you'll need access to a GPU, perhaps on a high-end gaming system. And it'll likely take hours to days worth of training time, depending on how much training data you have and the capabilities of your GPU. And then you'll have a trained face swap network. You still need to use that to produce the video. So you start with the trained network, and then the video that you wish to modify, and again, compute time on a GPU, a high-end gaming computer will do. And it might take minutes to hours, depending on the length of the video you wish to alter and the capabilities of that GPU to produce the result. So what's the technical approach that's driving the deepfakes community? One of the popular approaches uses a machine learning technique known as autoencoders, which have three key parts. The first is the encoder, the second is the encoding or the bottleneck, and the third is the decoder. It's the job of the encoder to take the high-dimensional input image and compress it down into a semantically meaningful representation in the encoding. And it's the job of the decoder to reconstruct that encoding to make an approximation for the input image. This gives us an unsupervised way to learn a semantically meaningful representation of the data. And by comparing the difference between the input and the output data, that provides us an error signal that we can use to update the weights in the network during training. So how is this used to make a deepfake? Essentially, two autoencoders are trained. Now, there's a subtle change here. The encoder is in common across the two people. So it shares weights and learns to compress both people to the same semantic representation. But two individualized decoders are also trained, one for each person. And then at production time, we take person A and we encode them, and then we use the decoder for person B to reconstruct the input image. That has the effect of swapping the faces across the two videos. So we've seen how you can create a manipulation using today's AI techniques. Let's think about how you might manually assess an image for manipulation. And in this case, it's a propaganda image from a military exercise. So starting at the top of the image, you can see two objects that are effectively identical, two hovercrafts moving through the same physical medium. However, they're having different side effects on the medium. In one case, there's a wake, in another, there is not. That inconsistency may be an indication of manipulation. Further down in the image, you can see two hovercrafts that are identical, even including the spray in front of them. This might be a clue that one was cut and pasted to create the other object instance. You can also look at other subtle clues in the image. So for instance, shadows. Are they consistent with where and when the image was acquired? We can estimate the sun angle knowing time of day and geographic position. We can also bring other assets to bear, as illustrated by the image inset in the bottom left-hand side. This is another image from the same military exercise, and it shows a different number of hovercrafts or a different number of objects in the scene. That inconsistency is suspicious and, again, might be an indication that the image has been manipulated. So that's how you can go about assessing an image manually, but that takes a long period of time, and it takes significant expertise to do that. It doesn't scale to the volume of data that we see on the internet. So the goal of the Metaphor program is to do this automatically, and we frame this around three levels of information. The first is digital integrity, which asks, are the pixels and the representations consistent or inconsistent? For instance, we might look at noise fingerprints that are characteristic of a particular sensor or camera. Or we might look at compression artifacts that indicate choices that were made in a JPEG implementation. The next level of information that we look at is physical integrity. Are the laws of physics violated? So we use the example of the wakes for the hovercrafts, but there's other things that you can look at as well. Are the lighting and shadows consistent? Is the geometry of the scene consistent with a camera that acquired it? And finally, the third level of information is semantic integrity. And that asks the question, is a hypothesis about a visual asset disputable? This is where we can bring to bear outside information. It might be other media assets or other things that we know are true. So for instance, the sun angle example. or we might look at weather for an image that was taken outdoors. We're also building automated approaches to reason across all these levels of information. In our last full-scale evaluation last summer, we had over 50 automated manipulation detectors. And so we seek to combine all that information to produce a single integrity score that captures everything that we know about a single media asset. So now I'm going to give you 3 highlights from the program, one for each of the integrity levels. At the digital integrity level, I'll show you a deep learning technique for detecting the addition of objects. At the physical level, I'll show a way to detect that a video may have been composited by looking at lighting on faces. And then at the semantic level, I'll talk about an approach for verifying the location and time of an image using weather information. These all use deep learning and AI techniques. So the first approach was developed by the University of Naples, and it uses a Siamese network which shares weights. It's trained across a set of pairs of image chips that are either from the same image and have consistent noise patterns, or are from 2 different images and have inconsistent noise patterns. This goes into a neural network with shared weights. A distance is computed across the noise print response of the network. That's what we're trying to train the network to do. And then based on that distance function, we can make a binary classification decision. Errors in that binary classification decision provide us information that we can use to update the weights in the neural network. So this is how we train the noise print system for digital integrity. Then when we receive an image that we wish to verify, we run that network on it. We produce a noise print, which is indicative of perhaps a particular camera or class of cameras. And we can cluster inside that noise print to see if there are regions that are inconsistent, which allows us to identify the object that was added in this case. In this example from physical integrity, we build a shape from shading network known as SFSNet in the slide. The goal of this network is to extract properties from faces that are automatically detected. So those properties include geometry, lighting, and reflectance. This is a multitask deep learning network. And it's trained with a combination of synthetic and real data. So then when we go to analyze a media asset, such as a video that might be a combination of 2 videos of the same scene, but with different individuals in it, we extract their faces automatically using deep learning-based face detection approaches, and then run a SFSNet on them. We look in particular at the lighting output of the network and see if it's consistent or inconsistent across the faces. If the faces in the scene have different lighting in them, that might be an indication that the video has been manipulated. Finally, at the semantic level, we're building networks to estimate weather properties from pixels alone. At training time, we take images that have known good locations and time. We use that metadata information to look up weather properties in the cloud, such as temperature and humidity. And then we build a deep network to estimate those same properties directly from the image. And by comparing what we know is true from the lookup from the metadata to what the deep network estimates, again, that provides an error signal that we can use during training to update the weights in the deep network. At test time, when we wish to assess an image that we haven't seen before, we use a similar process. This time, the metadata may have been tampered with, or the image may have been tampered with. But we use the metadata to look up the weather data, and that gives us one estimate of the weather properties. And then we use our trained network to estimate those same properties from the pixels alone. So that gives us 2 estimates of the weather properties, and we can compare them and see if they're consistent or inconsistent. Again, inconsistency may indicate that the image has been manipulated. So what does the future hold? In coming years, you may see technologies developed by the Metaphor program that enable accurate detection of manipulated media. Such capabilities could enable filtering and flagging on internet platforms, for instance, that happens automatically and at scale, and that are presented to you as a user. That gives us the ability to have much more comprehensive protection from media manipulation. Thank you, and I'll take questions.
Great. Thank you.
All right, so one of the questions is how do you see the detection technology continuing to evolve, potentially beyond even what's being explored today? So I think that's a really interesting question, right? We have a bit of a cat and mouse game going on here. We build better detectors, they build better manipulators, we build better detectors. So I think one of the things that we need to consider in that process of building better detectors is what is the supply chain for generating a manipulation? We talked about what it takes to create a deepfake. It requires compute, it requires training data. The more detectors we have that look at multiple sources of information, the more requirements we put on them for gathering training data, the more requirements we put on them for compute. Perhaps if we raise the bar high enough, then we'll take this out of the hands of an individual manipulator and put it again as a capability for higher resource manipulators. So I guess to paraphrase one of the other questions here, it's really going towards what's the intent of a manipulation. So the focus of the program is on detecting the manipulations, but we don't necessarily characterize them as malicious or not. So that is still a really hard problem. That requires significant insight into the semantic content of the image and a true understanding of the manipulation. So that might be an element of future work for us. And with that, I will thank you.